As mentioned earlier in this lesson, we said that the photoelectric effect is one of those experiments that you cannot explain by thinking of light as a wave. Okay? So here are some of the facts regarding the photoelectric effect. First of all, light, if you shine light on a metallic surface, it can cause electrons to get ejected. So here are your electrons, and here's your metal surface right here. Okay? And depending on the material that you use, the metal that you use, there's a threshold or minimum frequency, nu naught, that you need in order for electrons to be ejected. Basically, if nu is less than nu naught, less than the threshold frequency, you can't get any electron to eject, even regardless of how intense you make the radiation. And that's kind of anomalous because remember, we said the intensity of the radiation is related to the amplitude of the wave. The more intense the radiation, the higher the energy that that wave is able to deliver. It doesn't seem to matter how intense you make the wave. Okay? So that's anomalous. But even a very weak intensity, if it's got the right frequency, if the frequency is higher than the threshold, then you can get electrons to eject. Also, the maximum kinetic energy of the electrons that are ejected, you can measure the kinetic energy of these electrons that are ejected. Okay, these energies do not depend on how intense the radiation is. Again, it's anomalous because why wouldn't it be? You make the radiation more intense, you're providing more energy. Why can't you get more energetic electrons? But it does depend on the frequency. The higher the frequency, the higher the kinetic energy of the electrons that are ejected. Question is why? And that's the reason why the idea of photons was introduced. Okay. Anyway, the number of photoelectrons ejected is known to depend on intensity. So it seems like intensity has to do with the number of photons, not on the energy of the photons. Okay, so here's Einstein's explanation for the photoelectric effect, for which he got the Nobel Prize. Okay, Einstein said, imagine that light is a stream of photons. Each photon carries an energy equal to h nu, and that there's a minimum energy needed to dislodge an electron from the surface, and that minimum energy must be equal to h nu naught. So if nu is less than nu naught, then the photon energy is going to be less than that threshold frequency, threshold energy. That minimum energy is called the work function, phi. So this Greek letter phi is also known as the work function. So if the energy of the photon is less than what's needed to dislodge the electron, then you don't see any electrons. If it exceeds phi, then the kinetic energy of the photoelectron is what's left over. So h nu is the total photon energy minus the energy that you need just to pry the electron from the surface. The difference between the two, the residual energy, becomes the kinetic energy of the photoelectron. And like I said, higher intensity simply means more photons. Okay, so that does not affect the kinetic energy of the electrons that are ejected. Let's look at an example. Let's say you have a 300 nanometer radiation. If you calculate the photon energy for that, E equals h nu, okay, you'll find that that's 4.134 electron volt. Aluminum has a work function phi of 4.08 electron volts. What happens if you shine light with 300 nanometer radiation wavelength on a piece of aluminum metal? Can you get electrons to eject? Well, the answer is yes, because the photon energy, 4.134, exceeds phi, right? So h nu is your photon energy minus phi, the work function, 4.08 electron volts, gives you the kinetic energy of the photoelectron, which is going to be 4.134 minus 4.08, 0.054 electron volts. So this is going to be the kinetic energy of the electron that is ejected.